Hello. In a previous video as part of the integration playlist, we talked about integration by substitution and I worked through one or two examples. In this video I want to talk about integration by parts. This is another very important core skill in integral calculus. And well, I suppose you might ask, well, if we're going to be talking about integration by parts, why do you have the result for the differentiation of a product written at the top? And I suppose, this video isn't a proof. I'm not going to cover a proof of integration by parts or anything like that. But I suppose like the one of the important things to acknowledge is that integration by parts relies on the result for the differentiation of a product. And so what I mean is that if I just draw a line across here, let's just cut the page. And we know the differentiation of a product, right? Is if we have, for example, if we're taking the derivative with respect to x, and of course that's times uv, right? Where u and v are both functions of x. Well, what we get is exactly what we have right here. We have u times the derivative of v with respect to x plus the derivative of u with respect to x times v. And this is a standard, just basic result that one should already be familiar with. But when it comes to integration by parts, we can now integrate this result for the differentiation of a product. And when we integrate this, well, what do we find? Let's figure it out, right? So we have the derivative of x with respect to x. We integrate the left-hand side here. This is just going to cancel, so we're going to get uv on the left-hand side. And now we're integrating, and I'll just write it all out, we're integrating u times dv by dx. And of course, we're going to be integrating this with respect to x. We got to write that. And then we're plus we're adding and we're integrating here du by dx times v, right? We still got our v, and of course that we're integrating with respect to x. Right, now all we want to do is essentially rearrange this, and we are going to have our formula for integration by parts. And so here, notice we're just integrating du by dx times v with respect to x. We just want to subtract all of this on both sides, and what we end up getting is we're integrating u times dv by dx with respect to x, and this is going to equal, we still have our uv, u times v, so uv, and now it's we're subtracting, and here we're integrating du by dx times v with respect to x. This is integration by parts. As I said, it's not so much a proof, but all I want to do really is I just want to sort of, if anything, just highlight the connection. And then this is one of the great things about calculus, and the more that one works in calculus and learns higher, more advanced methods and things, that there's so much interrelation of all the with respect to the things that one has already learned, such as the chain rule. The chain rule, so many proofs and derivations rely on the chain rule. It's incredible. And here's another case, right, where we can think about integration by parts. And I guess that's the point I want to emphasize here, is that this is how I remember integration by parts. That for all intents and purposes, that it's just the integral of a product of two functions, where the first function is times the integral of the second, right? We have u and v. The first function is u. Our second function, we're treating it as dv by dx. It's the derivative of v with respect to x. And so what we want to do when we integrate by parts is we want to integrate this dv by dx, right? We want to get uv. Well, we already know u, if we're speaking very generally, so we just want to integrate our second function, and we're going to get uv, and then we're just going to derive our u, right? We're taking the derivative of u with respect to x, and we're just multiplying it by the v that we've already found. If that doesn't make a lot of sense, well, if I scroll down, let's just work on an example, and can just sort of reiterate the key idea, I suppose. Let's just say that we're asked to evaluate the integral. We'll just say I equals evaluate the integral. Let's do something that's somewhat fun, like I'll try to keep it textbook as well. Let's say x sine x with respect to x, right? Okay, so here we have two functions. Note, this is u, our x term here. This is u. We can mark that as u. Okay, this sine x term, this is our second function, but it's dv by dx, right? This isn't v, this is dv by dx. So we have to integrate this. So again, just remember, integration by parts is in the form of the integral of a product of two functions, right? And it's going to be equal to the first function times the integral of the second. The first function times the integral of the second, because we're treating the second function as its derivative. And then we're subtracting, so it's going to be minus, right? Minus the integral of the derivative of the first function, which is just u. We already know u. In this case, it's x. Times v, right, which we'll already find in the process. And so again, u is the first function. The second function you treat as dv by dx. And then just to find v, the integral of the second, it's just by usually just by inspection, right? We can integrate this by inspection. We don't need to write it all out. It's just a standard result. Okay, so let's just work through it. We're asked to evaluate this integral of x sine of x with respect to x. Here's our u, it's the x term. Sine of x is dv by dx. Okay, so what do we need? Well, let's just write it. I equals, when we integrate in this form, note x sine x is in this form right here, right? So we have our u, which is, we know, is x, times our v. Well, to get v, we just need to integrate sine of x. What do you get when you integrate sine of x? It's a standard result. If one thinks of the just basic table of integrals, it's going to be negative cos x. And of course now we're subtracting, so minus the integral. We're integrating, I should say, minus, and we're integrating here du by dx. Well, or u is x, right? So what do we get when we take the derivative of x? Well, that's just 1. And I'll write it out just to make it explicit. And now our v. Well, we already know v. We found v, right? So minus cos x. And of course, we have to integrate this still. So we'll have our dx at the end, right? We're still integrating all of this here on the right with respect to x. Okay, cool. So let's just clean it up. That's really all that we need to do. And so I'll just write it all out, okay, right? So to make it explicit, okay, so we have x times negative cos x. Well, this is just x. Oh, whoops, minus x cos x. Cool. And let's just use the distributive property here, right? 1 times negative cos x. So we're just integrating negative cos x with respect to x, right? This is just negative cos x. Cool, so we've got two negatives, right? So that's going to cancel. So now if we integrate just cos x, right, because it's going to become positive, we just integrate that, we get sine x, right? Again, that's a standard result. So this all becomes I equals negative x cos x plus sine x plus, and we'll just add our constant of integration. And this would be this is what we end up with if we were to evaluate the integral I equals x sine x. Now, again, it's just to remember, the key idea is just to remember, for practical purposes, integration by parts in the form of the integral of a product of two functions, right, which is just equal to the first function times the integral of the second. It's the first function, in this case it's x, times the integral of the second function, right? Because we just want to think of this second function as its derivative. That's exactly what we have written up here, right? U times dv by dx. And we have it in this form, then it's just very simple from this point, right? You just integrate your second function, so you get uv, and then you just minus and the integral of of the derivative u with respect to x times v dx. Now, I guess maybe I'll close the video by noting that it's not always so simple when it comes to the separation of the functions. Like in this case, it's very simple, right? We know, okay, we have x sine x. Well, one function, x here, that's our function u. Sine of x, well, that's dv by dx. That's a second function. It's very easy to separate these two, isn't it? But it's really not always so easy when one begins to sort of advance. And another way to put it is it's not always explicit or apparent. Like, you could end up with some crazy integrals. I don't know, like you could be asked to evaluate something like x raised, like let's just say x raised to the 5th power times, I don't know, e raised to the negative x, which is raised to the 6th power or something, right? So like it's not always so apparent how to separate these functions, but I'll save that for a separate video.